we want to look at trigonometric graphs of the form y equal r sine omega t plus alpha. So omega and alpha, those are Greek letters. In fact, the first letter of the Greek alphabet is alpha and the last letter is omega. And as you know, many times Greek letters are used for representing symbols in mathematics and science, right? But anyway, I want to look at them with regards to amplitude, period, and phase shift. Now, when you talk about amplitude, like you have your x and y axis and you have your sine wave, right? If you increase the amplitude of this wave, say double it, the maximum height will double, but it will still be in phase with the old graph. Alright, so the amplitude, remember, is the height from 0 to the top or to the bottom of the wave, whichever is the highest or the lowest part, right? The period is how long it takes to complete one cycle. So if you increase the period of this wave, it would look something, I guess, like this. If you double the period, alright? Oh, that's the wavelength you're looking at. But the period is how long it takes for one cycle to be completed. So if the wave is passing and it takes, let me erase the red one. Say it takes 1 second from here to here, right? If the period is doubled, that means it will take 2 seconds for one cycle to be completed. So 1 second, alright, 2 seconds, that means 1 more second. Alright, so it will be same as the red wave I had before, but I want to talk about it in terms of seconds. Let me redraw it because we did not change the amplitude. Amplitude remains the same, and I drew that one in a different amplitude. Alright, so if this wave is traveling this way at the same speed, and you have to wait 2 seconds for one cycle to pass you, then you're looking at going from here to here. So basically, I doubled the wavelength, which means you double the period of the wave. Alright, you double the distance that you have to travel to complete one cycle. You will also double how long it takes to complete one cycle, assuming you're traveling at the same speed. Right? Of course, if you halve the period, then you'd have to halve the wave length, which means in half second you're looking at a wave that seems more like this. Alright? So you see that? One cycle completed in half second. Alright. They didn't talk about the frequency. Right? If you half the wavelength, you double the frequency. It will take 2 cycles to complete where one cycle is if you double the frequency. But they didn't talk about the frequency here. What they talk about is the phase shift. So if you shift the phase of this wave, amplitude will remain. Let me do that again. It will be looking more like this, alright? That means if you started at 0 degrees and you shift the phase by 90 degrees, it means this would be your 90. Right? The phase is shifted to the right here. Now, we're going to see what the effect will be when it comes to R, omega, and alpha. Now, T usually would represent time, right? But this is the way that this equation is written generally in physics, right? Now, I mean, when you talk about, for example, sine wave in electrical, you might have it in a way such that you have y equal A for the amplitude, sine, then theta, say, plus some other letter, right? It may be alpha as well, but amplitude time R, y equal R sine alpha plus theta, or something like that. We wouldn't have the T here. Sometimes you see it written like this elsewhere, but we're going to look at this form of the equation, y equal R sine omega t plus alpha, plus or minus alpha. Let us see what happened here. I have a graph, or a blank page with a graph on GeoGebra. Let us do some plotting. You can't see the equation that I'm going to type. So I'm going to type it sine open bracket x. This is the form y equals sine x. Now this is our graph. Let me zoom in a bit. Let me shift it a bit to the left. Zoom in some more. So you can see the graph here. Let me make some changes to this thing. Oh, hold on. What was that? Sine x. Okay, properties. Yeah, the color is okay. I'll make the color stay. I'll increase the thickness. Alright, so we have the equation here. F of x equals sine x. That's how GeoGebra by default write their equation. So this is a graph. Now, here, I'm going to change R alone. So, what the graph is that we have is y equal sine t. GeoGebra calls it x. Alright? So, let us say sine x then. Because as you see, it's y equals sine x. What about y equal 2 sine x? What would that look like? Let's draw another graph. 2 sine x. Alright, our new graph, which is 2 sine x. I'm going to change the color. I'm going to increase the thickness. The red graph is 2 sine x. Notice, you go up The black graph, the original graph, what I call sine x, is at 1. But the new graph, 2 sine x, goes up to 2 from 0. And from 0, it goes down to negative 2. Alright, you see that? What about changing it so that we have half sine x? So let us say 0.5 sine x. You see that? The height is halved. So in that case, the r here represents the amplitude, which is the height, right, of the graph. So that's the amplitude. So the amplitude here is r. So you can see that. Now, suppose, alright, so y equal 2 sine x, what we did was double the amplitude. And for y equal half sine x, we half the amplitude. So you saw that r is the amplitude. Now let's go back to having only our original graph. So let's erase this graph and let us make a change to omega. Now here, when you have y equals sine x, let me erase some of what we did earlier. This is y equal sine of 1x. That's what it means. But let us, well, if I write it in this form, is really sine 1x plus or minus 0. That's what it is. But we didn't bother to write the 0 on the brackets. So what I want to do is look at y equals sine 2x. In this case, remember, the x is the t, the omega is the number you multiply x by. Alright? 2x. And by the way, let me rewrite it in this form. It's r sine omega x plus or minus alpha, right? Same thing. It's just that because I'm using GeoGebra and it says x instead of omega, I mean instead of t, we're looking at that in that form. So if you multiply the variable x by 2, what would happen? I'm going to have sine, open bracket, 2x, close bracket, and see what happened. Well, now we have our new graph. Let me change the color. Right. Oh, the thickness as well. I want it thicker. So here. Alright. What do you see happen when I say 2x? What we have here is a doubling of what? The frequency. And remember, if you go across, you have one cycle of the original block between these 2 points, right? The original graph. But the new graph, the 2x, you have 1 cycle, 2 cycles. So you completed 2 cycles here. So here now, what you have here. Alright, let me put frequency. Let me type frequency here. We look at the amplitude, frequency. So remember, frequency means how frequent it completes one cycle. Right? And you remember that this cycle is a set of changes that are completed and then what they repeat themselves over and over and over. So frequency is omega. So let me write that down. Omega is the frequency of the wave. Alright? Frequency. So you see that. Of course, having double the frequency, right, you have the period, because if it takes 1 second from here to here, and remember it's a cycle because you're increasing from 0, concentrate on the black graph, you're increasing from 0 at this point. The next time that happens, where you increase from 0 again, is here. So you complete 1 cycle. Now, when you double the frequency, what do you do with the period? Now, the period is the time it takes for 1 cycle to be completed. So, the red graph shows a doubling of the frequency. How long does it take to complete 1 cycle? It will be from here. Oh my, something happened a while ago. Let me undo that. That was alright. I accidentally shifted the red graph. So remember, going from here for the black graph all the way out here to complete 1 cycle. But for the red graph, you complete 1 cycle. Go right here. Half the time. Because for the red graph, you increase from 0 here. Here. The next time you increase from 0 again is here. That's 1 cycle. Alright. You could also remember that you could also complete the cycle between the 2 tops, the 2 peaks, where you're decreasing from maximum. Between here and here is a cycle as well. Right? I assume you knew these things already. So that's why I'm saying that you would remember, because you're expected to know about these things before. So you're dropping down from the top, from here, and you do it again here. Or you could measure the cycle between here and here. When you're rising from the bottom, you're going up from the bottom of the valley. The next time you do that again is here. Alright? So between here and here is a complete cycle. So we're looking at our cycle from where you rise from 0 and then you rise from 0 again. So that's doubling the frequency. So you half the period, and of course you half the wavelength, the distance that takes you through 1 cycle. So that's the frequency. Now, need to get rid of this now. We doubled the frequency a while ago. So frequency, omega. Alright. Now here, the period here, we said it was the time that it takes to complete 1 cycle. But the phase shift now, oh, by the way, the period that time to complete one cycle. If you double the frequency, you half the period, and so on. So the period is 1 over omega, all right, inverse. Now, here, when you, for example, have a frequency of 50 hertz, you want to find the period, it's 1 over 50. But in this case, remember, hertz is cycles per second. So, cycle per second. Now, that's the frequency. Now, the period would be 1 over 50 seconds per CYCLE, seconds per cycle, which is 0. What should it be? 0.2. 150 is 0.2. So 1 over 50 is 0.02 seconds to complete one cycle. So it's 1 over omega. Now let's look at the phase shift. Here, let's erase the red. This is y equals sine x. So I'm going to plot y equals sine. And by the way, let me write it here first. What I'm going to plot is y equals sine x plus 1. Y equal sine x plus 1. Alright? So it's sine x plus 1. Close bracket. Okay. Let me just make the necessary changes to this. The thickness, the color. Ha! Now, the thing is, if you can see the numbers on the horizontal axis here, they're not in degrees, they are in radians, alright? Now, when I say plus 1, the graph shifted to the left one place to the left. So suppose I put minus 1, what is that? Minus 1. Now the graph shifts to the right, one place to the right. Now that is called a phase shift. The phase is measured on the horizontal axis, the x-axis. So by shifting it, you're shifting the phase. So here, when you say plus 1, you go 1. Oh, let me rewrite that. You shift 1 to the left. So you go this way, one place. When you have y equal sine x minus 1, what this means, you shift 1 to the right. You go this way, one place. Alright? Now, you might have thought that if this one shifted it, the plus 1 would go to the right and the minus 1 to the left. But that's not so. It's somewhat like, say, for example, if I shift this, you're standing on the black graph, and the black graph shifts to the right. Or let's say you're in in a bus or you're in a car, sitting down looking through the window, and it's parked on the black graph, then the car moved one place to the right. The tree that you're looking at seemed like it moved one place to the left, it went back. So that's really what happened. Alright? And of course, if the driver reverses the car, you're looking at a tree outside, you look like the tree moved forward one place. Alright? So here, you're really on the black graph, and the black graph is what moves, but it's stationary relative to you. So the movement occurs with the original graph, the changed graph. Alright, it seems to occur with it. So here, saying you have y equals sine x. Y equals sine x plus 1 means the black graph move right. So this red graph move left. Alright? So here, let me just change so that I'm able to see the equation on the screen. Y equals sine x plus something, right? Plus or minus something. Alright, so I line it up. I want to shift it back one place, 1.0 something. Alright, so this is y equals sine x plus 1. You see that? And as I shift it to the right, you see when I pass the red graph, it turns negative. The number at the end is showing a movement upwards and downwards, but I want to try and move carefully and slowly so that I don't have a number at the end. It's 0.1 something. I want to make it x minus 1. It's kind of difficult to move it so that I get the exact x minus 1 again. Right? So here now, carefully moving it. My. It says 1.01. But let me go back to 1 exactly. Alright, so x minus 1 is to the right. So basically, what you have here is the phase shift. The phase shift occurs with the alpha. Alright? So, there you have that. I'll see you in the next video.